Hey everybody, welcome back. This is video 11, and in video 11 I'm going to share a couple of math things, dare I say it, right? In particular, I'm going to talk about the central limit theorem and the law of large numbers. And these are going to become potentially important for some of you who these are going to become important if you actually care how a margin of error or a confidence interval works next week. You will want to at least have these in your back pocket as sort of underlying concepts. You can certainly do the rest of the course without really understanding this video, but I don't 100% recommend it. In fact, I 0% recommend it. So let's talk about this stuff. I have a handy dandy script here because I want to make sure I am being clear. First, I'm going to have RStudio open for this so that I can show you a kind of animated demonstration. However, I am not, you don't need to open RStudio. You just need to watch and listen. Okay. Okay. So first, some things that are or should be in your make your own textbook. That is the terms distribution, normal curve, standard deviation. You already know what the mean is, right? That's the average. The central limit theorem and the law of large numbers. So as you're looking at the picture in front of you, and let me move it so that you can actually see the whole picture. Here we go. There it is. It says central limit theorem, but the first thing I want you to look at, there are dogs in my house. The first thing I want you to look at is the black line. So I'm tracing my mouse along this black line. This black line represents a weirdly distributed underlying population. And by distributed or distribution, I just mean what values are common in this data set. So along the y-axis, you see how commonly does each value appear. And on the x-axis, you see each value. So looking at this wavy black line, we see that there are very few values less than 0. A lot of values kind of centered here around 2 or 2.5. Very few values up through 10, and then another peak, but a shallower, wider peak at about 20. And that's just a random population of data that I made up. So the kind of shape of the data there, that rise and fall, how many observations have what kind of value, that is what a distribution is. The normal curve, I'm going to show you a different picture now. The normal curve is also known as the Gaussian distribution. You don't have to know that. Is a curve that describes a ton of natural populations. So it describes the distribution of heights in the human population. It describes the distribution of weights in most human populations. It describes the distribution of tree trunk girth. It describes, right, you can go on. And the normal curve is a bell-shaped curve. The best thing about it is that it can be described with only two numbers. First, the mean, the center point, and second, the standard deviation or the kind of width of the curve. So I'm going to show you a couple of different normal curves. So again, you don't need to be doing this in RStudio. This is just how I'm showing you stuff. So I'm going to make first a random normal population with a mean of 0 and a standard deviation of 1. And then I'm going to plot the distribution of that population. And it's going to look like that. Because it's not a huge population, it's not an extremely perfect normal curve. If it were a bigger population, it would likely have a much smoother curve. So we'll do that again. There we go. That's a bell-shaped curve. That is a normal curve. And again, it happens to be a normal curve with a mean of 0, right? You can see the big jump up in the middle and a standard deviation of 1. Here's another curve with a mean of 0 and a standard deviation of 2. I'm going to call that y. Oops. And I'm going to make that one show up on the same plot, but in blue. There it is. So as you can see, same mean, right? Same, and in a normal curve, the mean, the median, and the mode are the same because it's perfectly symmetrical. Same mean, same center, but much wider spread. So roughly speaking, a normal curve is a bell-shaped curve that is described by its mean or center and its standard deviation, or you might hear people use the term variance, or its variance, which basically means spread. So standard deviation, technically the square root of the variance, you don't care. Conceptually, you need to know that standard deviation and variance refer to how widely spread a curve is. Is it narrow or is it wide? And these are going to become really important concepts when we start thinking about confidence intervals. Okay, but let's look back at the central limit theorem. So I'm going to run this fancy thing again. We're going to draw a different picture. There's our picture. Okay, took a while to draw. Did you see that? That's because what I did in this picture was to take from the large, weird-shaped underlying population, I took 1,000 samples. And in each of those 1,000 samples, I recorded the mean, right? So I took the mean of a whole bunch of different samples, and then I looked at the distribution of those means. That's the red line. The central limit theorem tells us that no matter how bizarre the underlying distribution, if we take a bunch of samples, the means of those samples is going to be distributed normally, and it's going to be distributed normally right around the mean of the real population. So let me say that one more time. The central limit theorem tells us that no matter what the distribution of the underlying population, if we take a bunch of random samples, and by the way, the random samples are what's shown in the ghostly gray there. If we take a bunch of random samples and we record the mean of each of those samples, the distribution of those means is going to be a normal curve with the same mean as the underlying population. Okay, that was fun, right? Now you know that. And that fact about any distribution is going to be a sort of primary driver of the way that we interpret confidence intervals next week and in the weeks to come. So it's worthwhile to think about it. And don't worry if that sounds like gobbledygook. That is entirely possible. I totally understand. It takes a minute, but keep thinking about it. To remind you one more time, the heavy black curve is the population that I made up. The many, 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 many thin gray lines are samples from that population. And the red curve is the distribution of the means of those samples. Fun, right? No, not fun? Okay, well, guess what? I don't care. Okay. So next, the law of large numbers. The law of large numbers is, I think, easier to understand than the central limit theorem. What the law of large numbers says is that as your sample gets bigger, your sample mean gets closer to the mean of the population. I know, shocking. Here's a fun demonstration. I'm going to just draw a new picture here. All right, so here's my sample mean and my sample size. I have an underlying population with a mean that is approximately 50. It's that red line right there. And as I take larger and larger samples, right? So when I have a sample of 1 or a sample of 2, it's quite possible, or even a sample of 30 or 50, it's quite possible to end up with a sample mean that is, statistically speaking, not that close. However, as I get more and more, what you should be seeing is that, whoops, I'm going to go the other way. I'm going to go like this. Is that right for you? The distribution, again, that word, distribution, if as the sample size, that's the x-axis here, as the sample size increases, um, the variation or the variability of the sample mean is gets lower and lower and lower. That's all it is. Big samples give results that are closer to the underlying population. I know, shocking. Okay, that, friends, is the end of video number 11. So again, I encourage you to think about the concept of a statistical distribution, the idea of a normal curve, the central limit theorem, the law of large numbers, and mean and standard deviation. Okay, I know. It's a lot, but don't worry. We're going to do it 1,000 more times. All right, see you next time.